What exactly is the Wadati Benioff zone? Let's start with the core idea. The Wadati Benioff zone, sometimes just called the Benioff zone, is a sloping plane of earthquake activity that traces the path of a subducting oceanic plate as it dives beneath another tectonic plate. In simple language, imagine an oceanic plate sliding underneath a continental plate or another oceanic plate. As it bends and sinks, it doesn't go quietly. Instead, earthquakes occur along the top surface of that sinking slab, sometimes reaching extraordinary depths, a few hundred kilometers, sometimes even over 600 kilometers beneath the Earth's surface. These earthquakes do not occur randomly. They outline a distinct and usually narrow band that extends downward into the mantle. That band is the Wadati Benioff zone. What makes it special is this: it provides one of the clearest, most direct pieces of evidence that plates are actually moving, that subduction really happens, and that material from the Earth's lithosphere can descend deep into the mantle over time. So, in a nutshell, the Wadati Benioff zone is basically the seismic shadow of a sinking tectonic plate. A little history. Who were Wadati and Benioff? The name comes from two scientists working independently around the mid-20th century: Keiichi Wadati, a Japanese seismologist, and Hugo Benioff, an American seismologist. Keiichi Wadati. Back in the 1920s and 1930s, long before plate tectonics was accepted, Wadati made the remarkable observation that some earthquakes occurred far below the Earth's crust, at depths where scientists at the time didn't believe earthquakes could happen. He noticed deep events beneath Japan, aligned in a sloping pattern from shallow near the coast to deeper inland. His work puzzled many scientists, because classical geology at the time could not explain deep earthquakes. Hugo Benioff. Benioff later analyzed earthquake patterns across several subduction zones, especially around the Pacific. He realized these deep earthquakes formed a plane-like structure, dipping beneath volcanic arcs and marking the descent of a large slab of lithosphere. Together, though not actually collaborating, their discoveries painted the same picture. The Earth has deep earthquake zones associated with downward tectonic motion. When plate tectonics became widely accepted in the 1960s, the seismological evidence from Wadati and Benioff became a cornerstone demonstration that subduction was real. The geometrical structure of a Wadati Benioff zone. Let me now paint a mental picture of what the zone actually looks like. Imagine a tectonic plate boundary where one plate begins to dive under another. At the surface, you might see a deep ocean trench, like the Mariana Trench, the Peru-Chile Trench, or the Japan Trench. Now, if you could take an enormous X-ray snapshot of the Earth beneath that trench, you would see dozens, hundreds, or thousands of earthquake epicenters sprinkled below the surface, but not randomly. They form a narrow, dipping band, a plane that slopes downward from the trench at an angle anywhere from about 20 degrees to 70 degrees. This plane typically extends hundreds of kilometers into the Earth. In some places, the Wadati Benioff zone can be traced down to depths of 660 kilometers, which is around the boundary between the upper mantle and lower mantle, though the deepest reliably recorded earthquakes happen a bit above that depth, around 700 kilometers in exceptional cases. The key point is depth distribution. Shallow earthquakes, O-70 kilometers, near the trench and on the upper part of the slab. Intermediate depth earthquakes, 7-300 kilometers, further down along the sinking slab. Deep earthquakes, 300-660 kilometers, occurring within the slab as it penetrates the mantle transition zone. Together, these depths form a continuous, planar zone. That outline is the internal geometry of a subducting plate. Why do earthquakes occur in a Wadati Benioff zone? Now let's ask the fundamental question: why do earthquakes happen so deep underground? Near the surface, earthquakes make intuitive sense. Rocks are brittle. They break. Energy is released. But at hundreds of kilometers deep, The pressure and temperature are so extreme that we would expect rocks to behave plastically, not brittly. In simpler language, we'd expect them to bend and flow rather than crack and snap. Yet they do snap in certain circumstances. Here are the main mechanisms: slab dehydration and dehydration embrittlement. Oceanic plates contain water, both in sediments and within minerals in the oceanic crust and upper mantle. When the plate subducts, the increasing pressure causes these minerals to release water in a process known as dehydration. This released water reduces the effective stress on rocks, weakening them and causing brittle failure even at depths where the temperature would normally make that impossible. This mechanism is believed to explain many intermediate depth earthquakes. Transformational faulting, phase changes. As minerals in the slab descend, they undergo phase transitions. For example, olivine, one of the most abundant minerals in the upper mantle, transforms into wurtzlite and then ringwoodite under high pressure. Later, as temperature increases, ringwoodite transitions into perovskite and other forms. These transformations can occur suddenly, producing shear instabilities that lead to earthquakes. This mechanism is tied especially to deep earthquakes, like the magnitude -8.3 2013 Okhotsk deep earthquake. Slab pull and internal stresses. The sinking plate is pulled downward by gravity. As the plate bends, compresses, and stretches, large internal stresses build up. These can fracture the plate at depth. Although rocks are hotter and more ductile at depth, the slab is colder than the surrounding mantle, so it remains relatively brittle compared to the host mantle. This temperature contrast, known as thermal anomaly, helps maintain the slab's integrity and allows brittle failure. Interaction with surrounding mantle. Sometimes the slab encounters resistance or changes in mantle viscosity. At the mantle transition zone, around 410 km and 660 km depth, the surrounding mantle behaves differently. These viscosity jumps can create resistance, causing the slab to buckle or deform, generating internal earthquake-producing stresses. In short, earthquakes in a Wadati Benioff zone are the result of a combination of dehydration, mineral phase changes, thermal contrasts, and mechanical stresses acting as the slab dives into the mantle. How seismologists map Wadati Benioff zones. Modern seismology has turned the mapping of these zones into a highly refined science. Earthquake catalogs. Organizations like the USGS, IRIS, and the International Seismological Center maintain catalogs containing millions of earthquakes. Plotting the depth and location of events in subduction zones reveals the Wadati Benioff geometry directly. Seismic tomography. Like medical CT scans, seismic tomography uses the speed of seismic waves to image Earth's interior. Subducting slabs show up as fast, cold anomalies, often perfectly aligning with the plane of deep earthquakes. Double seismic zones. In some subduction systems, especially in Japan and Tonga, seismologists observe two parallel layers of earthquakes within the same slab. These are called double Wadati Benioff zones and may reflect dehydration processes occurring at different depths within the slab. Moment tensor solutions. By analyzing focal mechanisms, visualized as beach ball diagrams, seismologists infer the type of faulting at depth. These show patterns of downdip compression or downdip tension depending on slab geometry and sinking forces. Seismic attenuation and anisotropy studies. These studies reveal how the slab interacts with the mantle, and they often corroborate the precise position of the slab indicated by earthquake depths. The importance of the Wadati Benioff zone. Let's talk about why this concept is so central in seismology and geology. Evidence for plate tectonics. Before plate tectonics became widely accepted, one of the biggest mysteries was how to explain deep earthquakes. Once the Wadati Benioff zone was recognized, it provided unmistakable evidence that oceanic plates were being forced downward into the mantle. Understanding subduction dynamics. The angle, shape, and depth of the zone reveal The age of the subducting plate. The buoyancy of the slab. The viscosity structure of the surrounding mantle. Whether the slab penetrates into the lower mantle or stalls at the transition zone. These details are essential for models of mantle convection. Predicting seismic hazard. Although the deepest earthquakes rarely cause surface damage, shallow earthquakes in subduction zones are responsible for some of the largest and most devastating earthquakes known, like the 2011 Tohoku earthquake, the 2004 Sumatra Andaman earthquake, and the 1960 Chile megathrust earthquake. Mapping the Wadati Benioff zone helps locate the plate interface and identify locked zones where strain is building up. Understanding mantle composition and phase transformations. Deep earthquakes serve as probes of the deep earth. They let us infer mineral transitions, temperature profiles, and the composition of the slab. Clues to water transport into the mantle. Subducting slabs carry vast quantities of water into the deep mantle, and dehydration reactions associated with the Wadati Benioff zone reveal how water moves, how melts form, and how volcanoes are fed. Variations among subduction zones. No two subduction zones are alike. Wadati Benioff zones vary drastically among global locations, and these differences matter. Here are some major examples. Tonga Kermadec subduction zone, one of the steepest Wadati Benioff zones, produces some of the deepest earthquakes known. Represents extremely old, cold oceanic lithosphere descending rapidly. Japan subduction zone, complex zone with double seismic layers. Slab interactions create significant intermediate depth seismicity. Deep earthquakes sometimes reach around 600 kilometers. Peru-Chile Trench. Slab angle varies, shallower in some regions, flat slab subduction. Distance between trench and volcanic arc shifts accordingly. Cascadia subduction zone. Very few deep earthquakes. Slab is young, warm, and more buoyant. Wadati Benioff zone is weakly defined. Alaska subduction zone. Large, deep, and intermediate seismicity. Slab geometry complicated by subduction of large seamounts and plateaus. These differences reflect physical properties such as slab age, convergence rate, sediment thickness, composition, mantle dynamics, depth limits. How deep do earthquakes occur? A Wadati Benioff zone typically extends down to the 660 km seismic discontinuity. This boundary marks a major mineralogical change in the mantle. Deep earthquakes mostly occur above this level, although a few exceptionally deep events have been recorded. The reason deep earthquakes do not typically occur below 660 kilometers is that the slab is heated significantly by that depth and phase changes reduce the ability of rocks to store elastic strain. Still, the slab itself remains colder than the mantle for tens of millions of years as it descends. That thermal contrast is key to the persistence of deep seismicity. Case study example: the Japan Wadati Benioff zone. Let's explore a classic example to ground this discussion. Japan sits atop one of the most complex subduction settings on Earth, where the Pacific Plate subducts beneath the North American and Philippine sea plates. When seismologists plot earthquake depths across Honshu, they see a textbook Wadati Benioff zone. Shallow earthquakes near the trench. Intermediate ones 100-300 kilometers below northern Honshu. Deep earthquakes down to about 600 kilometers under the Sea of Japan. This dipping plane is inclined at roughly 30 to 40 degrees initially and steepens with depth. Here you see clear interactions between slab dehydration, mantle phase changes, and large-scale tectonic forces. Many of the greatest historic deep earthquakes have occurred under Japan. Another case study, the Tonga-Fiji region. This region produces the deepest reliably recorded earthquakes. It features very old oceanic lithosphere, greater than 120 million years old. Very fast convergence. A slab sinking almost vertically. Extreme internal stresses. Here, the Wadati Benioff zone is almost like a curtain plunging straight downward. Deep earthquakes have reached depths over 680 kilometers, likely due to the unusually cold nature of the slab. Theoretical and fundamental seismological implications. The existence of Wadati Benioff zones has led to numerous scientific insights. Slab penetration and mantle convection. In some regions, the slab penetrates the lower mantle. In others, it flattens and stalls at the transition zone. This affects the global pattern of heat transport, mantle flow, and volcanic activity. Slab anchoring and plate motions. The weight of cold subducting plates is one of the main drivers of plate tectonics. Mapping the Wadati Benioff zone helps quantify the slab pull force. Rheology, deformation behavior, of deep earth materials. Deep focus earthquakes help constrain the elasticity and breaking strength of rocks at high pressure and temperature. Without these earthquakes, we would know far less about how deep earth materials behave. Understanding double seismic zones. These zones offer clues about fluid migration, as one plane is often associated with dehydration reactions in the upper part of the slab and the other with bending or compression in the lower part. Deep earthquakes vs. shallow earthquakes. Why the difference matters. Shallow earthquakes, often caused by plate interactions at or near the surface, are the ones that cause tsunamis, building damage, and widespread hazards. Deep earthquakes rarely cause significant surface damage because the seismic waves lose energy on their long journey upward. But even though deep earthquakes are less destructive, they offer far more scientific insight. They help us look into regions of the earth that are otherwise completely inaccessible. They are natural probes revealing slab shape, slab temperature, mineral phase transitions, mantle viscosity, water content. So, while a deep Wadati Benioff zone earthquake might not be dangerous to people on the surface, it is incredibly valuable to earth scientists. Wadati Benioff zones and volcanism. Subduction zones are famous for producing volcanic arcs, chains of volcanoes like the Andes, the Cascades, Japan's Arc, the Aleutians, and others. The Wadati Benioff zone plays a central role in this process. As the slab dehydrates, water rises into the overlying mantle wedge. Water lowers the melting point of the mantle. Partial melting produces magma. This magma rises to feed volcanoes of the arc. Thus, the geometry of the Wadati Benioff zone helps dictate where volcanoes form, how far inland the arc sits, how deep melting begins. Typically, volcanic arcs occur about 100–150 kilometers above the slab at the depth where dehydration liberates sufficient fluids into the mantle wedge. What happens to the slab in the long term? We know the slab descends down the Wadati Benioff zone, but what happens afterward? Two major fates. 1. Penetration into the lower mantle. In some zones, like Tonga, the slab remains cold enough to sink straight through the 660-kilometer discontinuity into the lower mantle. It may eventually reach depths around 1000–2000 kilometers. 2. Slab stagnation. Elsewhere, like beneath Eastern Asia, the slab bends or pulls at the transition zone, failing to penetrate the lower mantle, at least initially. This stagnation can last tens of millions of years. These different behaviors affect mantle circulation patterns, heat flow, and volcanic systems around the globe. Modern research questions. Even though Wadati Benioff zones are well understood conceptually, many deep research questions remain open. What exactly triggers deep earthquakes? How do dehydration reactions operate at 300–400 kilometers depth? How much water does the slab carry into the deep mantle? Why do some slabs penetrate the lower mantle while others stagnate? How does slab geometry affect mantle plumes and supervolcano formation? Advances in high-pressure mineral physics, computational geodynamics, and global seismic networks continue to refine our understanding. Every time a large deep earthquake happens, seismologists learn something new. Bringing it all together, the Wadati Benioff zone is quite simply, one of the most important and revealing features in the study of Earth's interior. It is the seismic expression of a tectonic plate being forced downward into the mantle. Through its earthquake activity, ranging from shallow to intermediate to deep, it outlines the geometry of the slab, reveals how rocks behave under extreme conditions, and provides vital clues to the internal functioning of our planet. Without Wadati Benioff zones, we would have far less evidence for plate tectonics, far less understanding of mantle convection, and far less insight into deep earth materials. These zones tell us where subduction occurs, how slabs bend and fracture, where volcanic arcs will appear, how stresses evolve within slabs, and how water moves through the mantle. They are a natural laboratory, an extraordinary window into the dynamic engine that drives our planet.